Hi dear students, this is the fifth part of the fifth module of the subject ME 206 Fluid Machinery. In the last part we have considered the clearance volume concept, and we have derived an expression for the work done per cycle with the clearance volume. Now we will move on to the next topic, that is free air delivered. Simply it is known as FAD. FAD is the short form of free air delivered. Free air delivery is the volume of air delivered being reduced to free air conditions. So if the volume of air delivered is being reduced to the free air condition, then it is known as the free air delivery, free air delivered FAD. Now we have to know what is free air condition. So free air condition refers to the standard conditions and may be taken as 1 atmospheric or 1.01325 bar and 15 degrees Celsius or 288 Kelvin. So they are corresponding to this condition, that is 1 bar and 15 degrees Celsius condition is known as the free air condition. Actually, if this temperature is not given, then we have to assume this as 15 degrees Celsius. Otherwise, in the problem and all, if this temperature is given, free air condition temperature is given, then we have to calculate everything based on that particular temperature. If temperature is not given, then that means we have to assume temperature is 15 degrees Celsius for free air condition. Okay, or simply this condition, this is the standard condition corresponding to the sea level. Actually, standard sea level condition pressure will be 1.01325 bar and 15 degrees Celsius. So since density of, why we are choosing this free air delivery is just for the comparison purposes of the compressors. So performance, we have to compare the performance of the compressors, then there should be some measures for that. That's why we are choosing this free air delivery, because the reason is, if the same compressor is operated at different levels, at sea level, if the compressor is being operated, then that means its performance is depending on how much air is actually sucked into the cylinder. So at the low temperature or sea level condition, the density of the air will be much more compared to the density of the air at higher altitude. So if we calculate the volumetric efficiency of the compressor at sea level and at a higher altitude, then we will have the different values. So if we want to compare two different compressors, then both is to be the performance values, like volumetric efficiencies, are to be calculated at the same standard condition. That's why we go for this free air delivery condition. Okay, since the density of the air varies with altitude, different compressors cannot be compared using volumetric efficiency. What is volumetric efficiency, we will see in the next slide. Compressor at datum level, that is sea level, shall deliver large mass than the same compressor at high altitude. The reason I already told. At the sea level, the density of the air will be more. That means more air can be sucked into the cylinder corresponding to the intake condition. So the mass handled will be more compared to the same compressor at the higher altitude. At the higher altitude, the density will be less. That means less air is to be taken into the, less air is entering into the cylinder. So so if we are comparing two compressors, we cannot compare one compressor if we are analyzing the performance of one compressor at higher altitude, that cannot be compared with the performance analysis of another compressor at the low altitudes. So that's why we go for the free air delivery condition. Now from perfect gas equation, we have PA VA by TA equal to P1 into V1 minus V4 by T1. Here A is the properties of air at free air condition. This suffix A stands for the free air delivery condition. So PA means pressure corresponding to free air delivered, that is 1.01325 bar. Usually the PA will be 1.01325 bar on atmosphere pressure. VA will be the volume of the air corresponding to free air condition. This VA is actually the free air delivered. This quantity VA finally calculated will give free air delivered. So TA is the corresponding temperature. If it is not given in the problem, then you have to take it as 15 degrees Celsius. These values is correspond to the suction condition of the air or entry condition of the air into the cylinder. P1 correspond to the pressure of the air actually entering into the cylinder. V1 minus V4 is the actual swept volume by considering the clearance volume. So V1 minus V4 is the effective swept volume, and T1 is the corresponding temperature of the air entering into the condition, or simply 1 stands for the inlet condition of the air into the compressor and A stands for the free air condition. So from this equation we will get VA equal to P1 by PA into TA by T1 into V1 minus V4 That is the final equation for VA. So the free air is calculated using this equation, VA equal to P1 by PA into TA by T1 into V1 minus V4. So this equation is very important. If you want to calculate the free air delivered, then you have to go for this equation, VA equal to P1 by PA, TA by T1 into V1 minus V4. Okay. Remember, if this TA is given as some value, just like 20 degree or something like that in the problem, then you have to use that TA instead of this 15 degrees Celsius. If nothing is given, then you have to use 15 degrees Celsius as the TA value. Now next one is volumetric efficiency. Volumetric efficiency of a compressor is the ratio of the free air delivered to the displacement of the compressor. It is also called the ratio of effective swept volume to the swept volume. So this is the well-known expression for the volumetric efficiency, that is volumetric efficiency equal to effective swept volume divided by the swept volume. So that is effective swept volume is V1 minus V4 and swept volume is actually V1 minus V3. I think that PV diagram you will be remembering. I can show you the PV diagram. This is the PV diagram. This is the effective swept volume. From here to here is from 4 to 1 is the effective swept volume. So V1 minus V4 is effective swept volume and actual swept volume is V1 minus V3 without considering this expansion, that is the swept volume. So but by considering this expansion, so finally the suction will be starting from 0.4. So effective swept volume is V1 minus V4, and if you are not considering this expansion, then the swept volume starts from at 0.3 from this point. So V1 minus V3 is the swept volume. So this ratio of these two is the volumetric efficiency. Now from the definition we know that clearance ratio is given by clearance volume by swept volume. Clearance volume is the volume V3 and swept volume is V1 minus V3. So this is equal to VC, V clearance by VS, S stands for swept, and it is simply written as K, small letter K. Short form of the clearance ratio is K. So clearance ratio is clearance volume by swept volume, V3 by V1 minus V3. So this expression for volumetric efficiency can be written as V1 minus V4 by V1 minus V3. This can be rewritten as V1 minus V3 plus V3. See, I am adding a minus V3 here and adding a plus V3. So sum will be 0. So finally it will be V1 minus V4 only. So V1 minus V3 plus V3 minus V4 all divided by V1 minus V3. See this. Now I am taking first two term in bracket and the other one as the separate terms. So this becomes V1 minus V3 by V1 minus V3. So this will become 1, and the next term is V3 minus V4 divided by V1 minus V3. So this can be split up into two terms, that is first one is plus V3 by V1 minus V3. Now next one is minus V4 by V1 minus V3. So I have separated this term into three terms, three separate terms. Now the volumetric efficiency equal to 1 plus V3 by V1 minus V3 minus V4 by V1 minus V3. Now from the definition of the clearance ratio, we know that V3 by V1 minus V3, this term, this second term is actually K, clearance ratio K. So this equation becomes 1 plus K minus V4 divided by V1 minus V3. So that is equal to 1 plus K minus, this can be further simplified as V3 by V3. So this will be actually equal to 1. So no change in this total value. So V3 by V3 into V4 by V1 minus V3. Now rearranging this 1 plus K is as such here, minus this term is rearranged as V3 by V1 minus V3. So this term is taken as the denominator for this first V3, and this V3 is taken as the denominator for V4, this one V4. So the total becomes 1 plus K minus V3 by V1 minus V3 into V4 by V3. Actually V3 by V1 minus V3 is K. So this entire term becomes 1 plus K minus K into V4 by V3. Now for a polytropic process, we know that P4 V4 raised to n is equal to P3 V3 raised to n. This is general equation for a polytropic process. PV raised to n is equal to constant. Therefore, from this equation we will get V4 by V3 equal to P3 by P4 all raised to 1 by n. But P3 equal to P2 and P4 equal to P1. Therefore, the final equation instead of V4 by V3, we can write as P2 by P1. Instead of P3 I am writing as P2, and instead of P4 I am writing P1. So V4 by V3 becomes P2 by P1 all raised to 1 by n. So the final expression for volumetric efficiency becomes 1 plus K minus K into P2 by P1 all raised to 1 by n. This is the equation to calculate the volumetric efficiency. Okay. So please by heart it. This is a very important equation. For doing the problems and all, we will be using this equation. So please remember this equation. And the volumetric efficiency is also expressed in terms of free air conditions. So sometimes the volumetric efficiency is also this is the volumetric. This equation is actually the volumetric efficiency expressed in terms of the clearance ratio as well as the pressure ratio of the compression. Now the same can be expressed in terms of the free air condition, that we will see. From the expression of the free air, we know that PA VA by TA equal to P1 into V1 minus V4 by T1, which implies that VA equal to P1 by PA into TA by T1 into V1 minus V4. This we have already seen in the starting of the presentation. Now volumetric efficiency is VA by VC. The one more definition of the volumetric efficiency was this one. See, the volumetric efficiency of the compressor is the ratio of free air delivered to the displacement of the compressor. Free air delivered is nothing but VA, and displacement of the compressor is V1 minus V3. So the equation becomes volumetric efficiency equal to VA by VC. Actually, V1 minus V3 is the clearance volume. You can see V1 minus V3 is the clearance volume. This PV diagram is somewhere here. See, this is V1 and this is V3. So from V1, if you are subtracting V3, then you will get the clearance volume. See, V1 is the volume from this point to this. Entire volume is V1 from here to here. Now V3 is from here to here. So from V1 you are subtracting this V3, then you will get the swept volume. Okay, that is what is used in that equation. That swept volume means the displacement of the piston. That much volume is the correspond to the displacement of the piston. So the volumetric efficiency is defined as the free air delivered by the displacement of the piston, that is VC. VA by, that is actually equal to VA by V1 minus V3. So VA can be written as P1 into TA. This equation can be substituting. This equation can be substituted for the VA. So P1 TA PA by T1 into V1 minus V4 divided by V1 minus V3. Now, but V1 minus V4 divided by V1 minus V3 is equal to 1 plus K minus K into V4 minus V3. This already we have seen in the last slide. So hence the volumetric efficiency becomes P1 PA by TA by T1. This term is constant into, instead of this one V1 minus V4 divided by V1 minus V3, we are substituting this one 1 plus K minus K V4 by V3. Now we have seen that V4 by V3 is nothing but P2 by P1 all raised to 1 by n. So this volumetric efficiency becomes P1 by PA into TA by T1 into 1 plus K minus K into P2 by P1 all raised to 1 by n. So this is the another expression for the volumetric efficiency in terms of free air conditions. If in the problem and all, if the free air condition is given, then you have to calculate the volumetric efficiency using this equation. If free air condition is not given in the problem, nothing is mentioned in the problem, then directly you can use this equation, that is 1 plus K minus K into P2 by P1 all raised to 1 by n. Anyway, this is the standard equation, and you have to go for this equation only if in the problem the free air condition is given, then you have to go for this equation. Otherwise you can go for the other equation. And one more thing you have to notice, for finding out the dimensions of the cylinder, the above equations are not used. Instead, the equation based on the inlet condition only is used. Never use this equation to calculate the dimensions of the cylinder, like diameter. If you want to find the diameter of the cylinder, then never use this equation. In that case, if for the design purposes and all, you have to always use the volumetric efficiency equation as 1 plus K minus K into P2 by P1 all raised to 1 by n. But in the problem, if free air condition is specifically mentioned, then you have to go for this equation. While doing the problems and all, I think it will be clear for you. Now we have to see one more thing, that is efficiencies of the compressor. So few efficiencies are mentioned here. First one is isothermal efficiency. Isothermal efficiency is the isothermal work done divided by the indicated work. We know that the isothermal work done is given by P1 V1 ln P2 by P1. This equation we have already derived, and indicated work done is the work done corresponding to the polytropic process. So it is given by n by n minus 1 P1 V1 P2 by P1 all raised to n minus 1 by n minus 1. This was the equation. So the ratio of these two quantities is simply known as the isothermal efficiency. Please remember this equation. This is an important equation. Now next one is mechanical efficiency. Mechanical efficiency is indicated power by the brake power. Now indicated power is given by Pm into LAN by 60 into small n. This equation P where small n is the number of stages. Sometimes the compression can be in 2 stage, 3 stage, something like that. So in that case, the n value is, if it is 2 stage, n is 2, 3 stage, 3, like that. If compression is in single stage compression, then n value is 1. Now n is the number of stages, and Pm is the mean effective pressure. Pm is the mean effective pressure. All other values are known. L you know, area of the cylinder you know, n is the number of revolution per minute, RPM. By 60 it is just to convert into second. So all other terms are known. N is the number of stages and Pm is the mean effective pressure. So if you want to use this equation, then we have to find out the mean effective pressure, and mean effective pressure is found mathematically dividing the work done per cycle by stroke volume. So this is the equation to find the mean effective pressure. You just calculate work done per cycle. You are having the equation to calculate the work done per cycle in different cases, isothermal cases, polytropic, isentropic cases, everything you know. The different equations are there to calculate the work done per cycle. First to calculate the work done per cycle, then divide that quantity by stroke volume, then you will get this value Pm. Now using this equation we can calculate the mechanical efficiency. Mechanical efficiency is actually indicated power divided by brake power. Indicated power is obtained from this equation. That is the work done per cycle corresponding to the polytropic process called the indicated power. Okay. Now brake power, it will be given in the problem. So or indicator power is calculated using this equation also, mean effective pressure into LAN by 60 into N. Any equation can be, any equation out of this, anyone can be used to calculate the mechanical efficiency or indicator power, no problem. Now next is volumetric efficiency, that already we have seen. It is defined as effective swept volume by swept volume. It is defined as V1 minus V4 divided by V1 minus V3, and it is given by 1 plus K minus K into P2 by P1 all raised to 1 by N, where K is the clearance ratio. And I have already told you, if the free air condition is not given, then you have to go for this equation. If free air condition is to be considered, then you are having the another equation, that is P1 by PA into TA by T1 into 1 plus K minus K into P2 by P1 all raised to 1 by N. Here P1 is the entry condition or inlet condition to the cylinder. TA, PA and all, it is the free air delivery corresponding pressure and temperature. Okay.